Okay, so the next problem, 17.3. So it's chapter 17. We're talking about Ohm's law and resistances. So these laws are fairly straightforward, so this might go pretty quickly. We're talking about the Bohr model of the atom. So what that is we have an orbit of an electron, right, around a nucleus. And so we're told that the electron orbits in a circle around the nucleus at this speed, right, with the radius of 5.29 times 10 to the negative 11 meters, right? And we want to find the current of that electron around the nucleus. So because of the way this model works, because we have a charge, we have, like, let's say, a particle moving in a circle consistently, right? This is an oscillation. So let's look at current as the charge over time, right? Well, we also have the charge over, it's going to be the period of the oscillation. And if we can recall from basic mechanics that a period of an oscillation is 2 pi over the oscillation speed. Now, also from basic mechanics, the oscillation speed is v over r. So that means that our period is going to be 2 pi r over v. Well, let's plug this in here, and that's going to give us the charge over 2 pi r over v, right? And this is just going to be our total charge. Where charge is going to be for the electron, right? So now, what do we have? We have 1.6 times 10 to the negative 19 coulombs. That's the charge of the electron, times, we're told, 2.19 times 10 to the 6 meters per second. Excuse me. This is all over 2 times pi times 5.29 times 10 to the negative 11 meters. That's the size of the orbit, right? Plug all this in, and we end up with 1.05 times 10 to the negative 3 coulombs per second, which is also this, coulombs per second is equal to an amp, by the way. So you can just rewrite it. The current for this, for an electron moving around in orbit around a nucleus, is, what did I say? Times 10 to the negative 3 amps. So that's the answer. Next problem. We're given a scenario where a person touches a piece of metal and there's a static shock, right? And that happens when we exceed a certain current. So we're given 80 microamps. So if we exceed this, then we are going to get a shock. It's going to come out as like a shock, right? So we want to know what is the electric potential difference for two different scenarios. For the resistance of a finger that is dry, we're given this resistance in ohms, and for a finger that is wet, we're given this resistance. Okay, all we really need to do here is use Ohm's law. V is equal to I times R. Voltage is equal to current times resistance. Ohm's law. That's worth remembering. Okay? So we're going to have V is equal to, for the first scenario, we'll say this is scenario 1, 80 times 10 to the negative 6 amps. That's what we're given. That's the current times 4 times 10 to the 5 ohms. That's going to equal 32 volts. For scenario 2, same current, because that's what we were given, times the resistance that we're given for the wet finger, 0.16 volts. So it's actually really interesting because if your finger is wet, the maximum voltage is much, much, much lower. So, okay, moving on. Next problem. We're given that for a typical battery, we have a current 0.15 amps. Okay, we're asked to find the number of electrons per hour. Okay, so, well, we have our standard formula for current. We want to know, it's important to find the number of seconds because that's a SI unit. So we need 60 seconds times 60 minutes times, yeah, that's it. That's equal to 3,600 seconds per hour, right? Anyway, so 3,600, that's what we're going to write down. Let's get that out of the way. So T is equal to 3,600 seconds per hour. Now we want to know what the number of electrons are. So the number of electrons. So, well, in our formula, this one up here, try not to make a mess so you can see what I'm doing. This one up here, this delta Q is the total charge. So the total charge is actually going to be the total number of electrons times the charge of the electron, right? So that's going to be equal to the total charge. So now here's what we got. I is equal to N times the charge of the electron over 3,600 seconds. So then if we rearrange everything, we're actually given this value for I, right? It's 0.15 amps. So, 0.15 amps. So I'm just rearranging, just doing a little bit of algebra. So now we've got 3,600 seconds times 0.15 amps over the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs. And we plug that in, we get 5.4 times 10 to the 21 electrons. I'm just going to write it down as E's. Electrons per hour. That's how many move in this battery. That's a lot. It's a crazy amount.